What if your software could just heal itself? I mean, really. Today we're going to break down Erlang and OTP. It's this whole programming world built from the ground up for exactly that. We're talking about building systems that are concurrent, super resilient, and, well, they almost never need you to hit the restart button.
All right, so let's start with a question that, honestly, every single software engineer has wrestled with. You know the pressure, right? That push for 5 nines of uptime. It's intense. So the big question is, how do you actually get there? How do you build something that just never fails? Like, is it even possible to write code that's totally bulletproof?
And this is where Erlang just flips the whole problem on its head with this brilliant, kind of counterintuitive answer. The secret isn't trying to prevent every single crash. I mean, that's impossible, right? The philosophy is to just accept that, hey, failures are going to happen. So instead of trying to build something that's totally unbreakable, you build it to recover. Gracefully, automatically, every single time something breaks.
So to really get how this works, we're going to walk through the key ideas behind Erlang and its amazing framework, OTP. First, we'll hit that let it crash philosophy. Then we'll look at the tiny little processes that make it all possible. After that, we'll see how they talk to each other, build up that supervisor safety net, check out these reusable patterns called behaviors, and then we'll put it all together.
Okay, first up, this whole let it crash idea. I know, it sounds kind of reckless, right? But it's actually an incredibly disciplined way to build software that can take a punch. The whole point is to box up failures, to contain them, so one little problem doesn't burn down the entire house.
And this quote right here introduces the magic ingredient, the supervision tree. So picture this. Instead of littering your code with endless try-catch blocks, you have these simple little worker processes. Their only job is to do their one thing. And if one of them fails, it's not its problem to figure out how to recover. Nope, that job belongs to a special supervisor process whose only purpose in life is to watch over it.
Now, this whole idea, this supervision tree thing, it only works because of how Erlang handles work, and that's with its fundamental building block, the process. But hold on, these are not the big, heavy operating system threads you're probably thinking of. Not even close. They are something completely different.
And here's the absolute game changer. Erlang processes are ridiculously lightweight, and they're totally isolated. Each one has its own little bubble of memory, which means a crash in one process can't mess up any of the others. They're so cheap to create and get rid of that you can literally have hundreds of thousands, even millions of them running all at once. And that massive concurrency is the secret sauce that makes the whole let it crash thing possible.
Okay, so you've got all these tiny, isolated processes zipping around. How in the world do they coordinate? And maybe more importantly, how do they keep an eye on each other so we can have that fault tolerance we've been talking about? Well, that's where these 3 things come into play: signals, links, and monitors.
First up, we've got links. You can think of a link as a pact, a blood pact almost, between two processes. It's basically them saying, look, we're in this together. If you crash for any reason that's not, a normal shutdown, I'm going down with you. It creates this shared fate, and that's super useful when you have two processes that absolutely cannot function without each other.
And then you have monitors, and these are a totally different beast. A monitor is just a one-way street. It's like one process telling another, hey, I need to know if you die, but your fate is not tied to mine. So if that process it's watching suddenly dies, the monitor process just gets a little down message about it. It doesn't crash itself. And you can probably see where this is going. That makes it absolutely perfect for a supervisor.
So just to put a fine point on it, links are all about shared fate. If you go, I go. But monitors, they're just about one-way observation. And it's that one-way, I'm just watching you mechanism that a supervisor needs to do its job without getting dragged down into the chaos.
All right, now let's put it all together and see how this builds the famous supervision tree. This is really the heart and soul of how OTP does fault tolerance. This is where everything we've just talked about clicks into place.
And the pattern itself is it's so simple, it's beautiful. You've got a worker process, right? It's just doing its job. Then you've got a supervisor process, and its only job is to watch that worker. So if the worker hits some weird bug and crashes, boom, the supervisor gets the notification, it looks at its rulebook, its restart strategy, and most of the time it just spins up a brand new, perfectly clean version of that worker. Just like that, the system has healed itself.
But wait, it gets even cooler.
Supervisors don't just watch workers. They can watch other supervisors. And this lets you build this amazing hierarchy, this tree of responsibility. So a failure way down in one tiny little leaf of the tree, it gets handled right there by its local supervisor. The problem doesn't spread up the chain and take down the whole application. The blast radius is totally contained.
Now, you could totally build all this stuff from scratch every time. The supervisors, the workers, all that logic. But man, that would get old fast. And that's exactly why OTP, the Open Telecom Platform, gives us these powerful building blocks called behaviors. They make everything so much easier.
And what this quote is really getting at is a super important design principle, separating the generic, boring boilerplate code from your actual, specific business logic. Think about it. OTP has already solved the common problems, like how a client-server model should work or how a supervisor should behave. They baked all that into these behaviors. All you have to do is fill in the parts that are unique to your app.
Let's make this real with an example. Okay, so here we have a pretty simple server, just written in plain Erlang. See how the generic server stuff, that receive loop, is all tangled up with the specific logic for what this server actually does, allocating and freeing channels? It works, sure, but it's a mess to reuse.
And here's the after picture. See? The code is now split in two. All that generic server loop logic, it's been moved into this reusable server.url module. Think of it like a mini version of OTP's famous gen server. And our specific logic, the channel stuff, is now in chat2.url. All it has to do is implement that handle call callback. It's beautiful. We just provide the what, and OTP handles the how.
So the big takeaway here isn't just that the code looks prettier. It's that you're building on top of this absolutely battle-tested foundation. OTP gives you these standardized, super robust ways to build supervisors and servers. Your own code immediately becomes easier to read, easier to maintain, and you basically get to inherit decades of hard-won wisdom about how to build systems that don't fall over.
Okay, let's zoom out and put all these pieces together. Let's look at the complete picture. This is how you design a system that isn't just patched to be resilient, it's resilient in its very DNA.
So you have this incredible layered cake of resilience. Right at the bottom, you've got your millions of tiny, isolated processes. On top of that, you have the links and monitors that let them watch each other. Then, supervisors use those monitors to build that amazing self-healing hierarchy. And finally, behaviors wrap it all up in these standardized, reusable packages. You see? Fault tolerance isn't some feature you tack on at the end. It is woven into the very fabric of the application from the start.
And that right there is the powerful idea I really want to leave you with. Erlang and OTP, they force you to think differently. It's a complete paradigm shift. It stops being about this impossible quest for perfect code that never, ever fails. Instead, it's about building systems that expect failure, that treat it as just a normal everyday event. And because they expect it, they have a clear, automatic, and super robust plan for what to do when it happens. And that is how you build software that can run for years and years without anyone ever having to touch it.